All right. So this is the Spring 213 test we're now going to work through. So in this particular version, there was a sample of the waves. I think yesterday I just copied it and used it for that. Let's knock out the multiple choice. As you can see on the first page, it's a whole bunch of constants. If I don't give you the value, you're either going to have to look for it or solve for it or ask me for the value. Most likely these values will be given to you. Number 1. Pressure tire gauge reads 2 atmospheres. What is the total pressure of the tire? 3. Rho, or density of a block of material, is what? A. Now, if I was talking about lambda, that would be what? Mass over length. And that is also, what is lambda typically called? Linear mass density, that's what I was going for. What you were just said, D is what symbol? That is sigma. And that is the area mass density. So you have a string which, when plucked, is 400 hertz. You tighten the string. Which one of these is the possible frequency? 800. It increases. Which string is vibrating at its second harmonic? Second harmonic is which string? String 5. You measure the spring constant of a spring on the moon, it's 300 newtons per meter. You bring it to the Earth, which has a greater gravity. The spring constant is now 300. It's a spring constant, it doesn't change. A string vibrates at its third overtone. How many antinodes are there? There are 4. So the third overtone is which string? Third overtone? Yeah. So that would be 1, 2. String 2 is the third overtone. You put your thumb over half the opening of a garden hose. The water's velocity increases. How many nodes are on string 2? String 2 has how many nodes? There are 5. There are the 2 on each end, or there's the 1 on each end, which is 2, and then the 3 in the middle. And then that will be eliminated. A simple pendulum has a period of 2 seconds. You quadruple the mass. The new period is what? 4 seconds. Oh! Oh, it is 2 seconds. What? There's no mass dependency on it. Mm-hmm. That's a sneaky dude who wrote that one. Which string has only 2 antinodes? 5. So 5 is D. Lambda is, we talked about this, mass per unit length. Units of pressure, Pascal. So units of pressure are either Pascal, newtons per meter squared, or atmospheres. One of the 3. You bob up and down 20 cycles in 10 seconds, your period is C, half a second. Strings are of identical length. Blah, blah, blah. They're at the first harmonic. One is thick, one is thin. The thicker string has what? Lower frequency. What is the equation for frequency of sound heard by an observer moving towards a source? So it's moving observer towards. So it's a I just heard all the answers. So it's a moving observer. So the parentheses are in the numerator. So we're down to A and E. It has to be E. And why is that? You're moving towards, so you're going to hear a higher frequency. Which one of these will produce a heard frequency that's greater than the source frequency? It has to be this one, the one that adds. The velocity of sound in a vibrating string is A. For a string, the first overtone is the same as the second harmonic. Quick question. The first overtone on a half pipe is the same as what harmonic? The third, yes. Which string only has 2 nodes? It's going to be 3. You bob up and down 20 cycles in 10 seconds. Your frequency is B, 2 hertz. String's first harmonic is 400 hertz. You loosen the string, which is an allowable frequency? The 300 hertz. Object is negatively buoyant. Which of the following is true? B. At the node of a vibrating string, which of the following is true? C. It does not move up and down. The parts of the string which move the most are called what? Antinodes. String vibrates at its second harmonic. How many nodes are there? So which one of these? So second harmonic is which string? 5. So how many nodes are there? There are 3. Hooke's law in vector form is what? E. Neutrally buoyant means what? D. All right. What we're going to do now is the great Walking Dead test. The story behind it is a couple of students came to my class or came to my office every Monday after a new episode of Walking Dead, and so we wanted some zombie questions. Now, walking undead zombies on a test would look grotesque, so that's why I used the Plants vs. Zombies. In the first problem, how do you use this 50-kilogram zombie to create a simple pendulum with a 7-second period? So it's a simple pendulum. So T is 2 pi L over G. Now, once again, we're on the planet Earth unless I say otherwise. So I know what gravity is. I know what the period is. So effectively, I'm asking for what's the length of a 7-second period simple pendulum. So T squared is 4 pi squared L over G. L is period squared g over 4 pi squared. 7 squared, 10, 4 pi squared. Now the numbers that pop out are not going to be all happy and nice and whole. 490 divided by 4 pi. So the length is 12.4 meters. So you're going to hang a zombie from a 12.4 meter string, and then that's the simple pendulum. If you've got a spring pendulum with the frequency of 12 hertz, that period is 2 pi m over k. I give you the frequency, so 1 over f is period, so 2 pi m over k. I give you the mass of the zombie. It wasn't useful in the first part, but now it is. The only thing that we don't know is k. So solve for k. 1 over f squared 4 pi squared m over k. Therefore k is 4 pi squared mf squared. So 4 pi squared 50, 12 squared. So the spring constant is 2.84 times 10 to the 5th newtons per meter. And that's the K. So that's the appetizer of the Walking Dead test. Now, problem 1 is a lot like the problem that we talked about yesterday. This happened right after Glenn was on top of the garbage dumpster, and his buddy just shot himself in the head. And so Glenn fell into the pool of zombies. And this is at the time, this was my theory of what happened. He fell into a sewer right underneath that dumpster and then made it to Maggie. Because I don't kill Glenn. Glenn is, well, Negan killed him, but spoilers, I know. So this is, you've got water at 1 atmosphere and moving at 2 meters per second. Now, one of the questions that people asked is, if Glenn is falling through this pipe, 12 centimeters is a bit of a stretch for Glenn to fit in, but 3 centimeters at the bottom, that's just going to be impossible. I'm sorry. I don't believe this. And I'm like, just deal with it. Let's just, that's not the point. It's a classic Bernoulli's equation problem with the equation of continuity. Equation of continuity is A1 V1 is equal to A2 V2. So V2 is A1 V1 over A2. Now both the pipes are circular. Area of a circle, pi r squared. So this becomes pi r1 squared V1 over pi r2 squared. What I'm going to do now is I'm going to show you a little bit of it's not a trick, but it does freak people out when I do it. Plugging it in right now, I use 12 squared 2 over 3 squared. And that's very interesting because I'm using both centimeters and meters within the same problem. And I don't have an issue with that, and I'll tell you why. R1 squared is going to cancel with the units of R2 squared. So it doesn't matter what units you put in there as long as R1 and R2 have the same units. So if you converted it to meters, you'd still get the same answer. It doesn't matter. V1, on the other hand, you're going to need that in meters per second because that's what I want. And this becomes it shoots out at 32 meters per second. And please, I don't want a negative. This could be, hold on. And just as a reminder, really, these things are me going over old tests and reminding myself what are the things that I need to avoid. And the thing that I will avoid on tomorrow's test are problems where the numbers are nonsensical. I'm gonna get these right, I promise. After 7 years, I think I should get it right eventually. Now that we've solved for the velocity, I need the pressure. And the pressure is specifically asked for in atmospheres. If I don't state it on the problem, you have the right to ask what form of variable do you, or what form of unit do you want this thing in? So I want it in atmospheres, P1 plus rho GH1 plus 1/2 rho V1 squared, P2 plus rho GH2 plus 1/2 rho V2 squared. So that's Bernoulli's equation. The bottom of the problem we use as the height of 0. Really, the only thing that matters is the difference. So that will be 0 and H1 will be 20. I'm looking for P2. So P1 plus rho GH1 plus 1/2 rho V1 squared minus 1/2 rho V2 squared is equal to P2. Now I want this answer to be given in atmospheres. Rho GH and rho V squared give their units in newtons per meter squared. So I have to change this to that. I factored out a rho just for the sake of making things a little bit easier. Yes?
On the test, you probably can't answer this, but will you, if you're wanting an atmosphere, will you always make it where pressure 1 is already an atmosphere and the rest of them are not an atmosphere?
I'm going to make it, most likely what will happen is that P1 or P2, whichever is given, will be in atmospheres. And then I will either ask for the final answer to be given in newtons per meter squared or atmospheres. It's going to require a conversion.
But will you make it, are you going to make it to where like all of them besides one of the pressures needs to be changed?
One of two things is going to happen. Either you're going to have to do this or multiply P1 by that. So it's got to be, if I ask for atmospheres, you use this. If I ask for newtons per meter squared, you'd have to do that. So it's one of the two. I'm not going to give the pressure in newtons per meter squared, and then everything just works out fine. I'm going to require that bit of knowledge. So continuing from here, P1 is 1, 1,000, 10. H1 is 20. V1 is 2. V2 is 32. That 32 really bothers me. I don't think this is going to be a negative number. It is a negative? Yeah. So let's just roll with it. The thing that I would do, and really what I'm doing here is I'm just kind of proofing these problems going, I need to fix that if I put that on the test, is that I would make the bottom pipe a lot bigger. It may have been at the time, I can't remember what I did. It may have been at the time sometime at the beginning when I go, whoops, there's a big mistake, I'll call an audible at the line and go, all right, it's not 3 centimeters, it's 3 meters. Or change it, or I'll officially tell the class, you're gonna get a negative number, don't be upset by it. No, not that. Yeah, so this ends up being, the answer is negative 3.06 atmospheres. Okay. What I did, I'm sorry, so that's 2. So this whole thing over here is negative 3.06. Add 1 to it, it's negative 2.06. The answer's still squirrely. And what I would do then is, I would just say you're gonna get a negative number. If you get a negative number, you got it right. The other part of the problem that I asked for, how many cubic meters of water passes through the pipe in 40 seconds? That's a flow or continuity problem. The volume is the flow times time, which is area 2 velocity 2 times time. I'm looking for how many cubic meters. Now, in this particular case, the units have to be in meters because I'm asking for cubic meters. So area 2 is pi times 0.03 squared. V is 32. Time is 40. So I get 3.62 cubic meters. And so that's the final volume. Okay. I'm going to save problem 2 after problem 3 because I love problem 2. Problem 3 is the Daryl problem. He's on a motorcycle. I never quite could understand why he rides around in the loudest thing possible. You're just begging for zombies to fly out at you. You hear 1300 and 1110 as he's coming and going. I need to know the speed of Daryl on the motorcycle, and I need to know the frequency of the motorcycle itself. This is a classic roulette wheel problem. You've got the frequencies coming and going, so it doesn't really matter if it's towards, over, away, or away, over, towards. It's still gonna cancel out and do the right thing. The motorcycle is the source, so it's a moving situation. So the frequencies that you have are F over 1 minus V over Vs, and then F over 1 plus V over Vs. Those frequencies cancel, and I'm left with 1 plus V over Vs, 1 minus V over Vs. And so that is the first step. Velocity of sound on the test will be 350 meters per second, just so that the numbers work out better. Cross multiply. And I get that. Distribute. This is something that you will have to do on the test. So know all the steps. You cannot say a miracle occurs. Get the V's on one side, non-V's on other. Factor. Solve for V. And you get that. So now you plug and chug. 350, 1300, 1110, 1300, 1110. And that will give you 27.6 meters per second. The last part of the problem is we have to figure out the source frequency. You can use either towards or away, because now you know what velocity is. We'll use towards. Solve for F. Plug and chug. 1300, 1 minus 27.6 over 350. And that gives me a frequency of 1197 hertz. And that is problem 3. Now on these tests, there tends to be a problem where we push the boundaries just a little bit to see if your problem solving skills are truly starting to advance. This problem pushes those boundaries and gives it a little nudge. It's an Atwood string, which means that we have to deal with a lot of stuff. First, the frequency of the string is NV over 2 big L. Big L currently, well, what I'll do is I'll write it NV over 2L1. The length of the vibrating string, that's what the big L is in the general equation. That big L is actually L1. The velocity is the tension over linear mass density. So this becomes N over 2L1 square root of tension over lambda. Tension is the mass that's hanging times gravity, because we know from sum of the forces, which is 0, which is equal to tension minus hanging mass, gravity, we get this. Lambda is the mass of the string divided by the total length, which is L1 plus L2. Plugging this stuff in, you get N over 2L1 square root mhg L1 plus L2 over ms. And that's the frequency. Yes.
Oh, I have a question.
Uh-huh.
Is L1 always going to be the vibrating string?
It depends on how I label it, but the vibrating part of the string is always between the wall and the pulley. I could say L sub zebra, and that's still, then you just use that. What it's called is not important. Now we have a couple of problems. One is the bucket of brains is the bucket itself has no mass, but there are a finite number of brains. You also know that I didn't specifically give you the brain mass, I just gave you a mass ratio. I said that one brain's mass is 1,000 times the mass of the string. All right, so this is pushing some, we got to read into this and problem solve. I was frequently asked, are you serious about this? Is this a correctly constructed problem? And I said yes. The hanging mass is N times the mass of the brain, because you got to have N brains in it, and this then becomes N over 2L1 M brain times N G L1 plus L2. Well, that's great and all, but I still don't know the mass of the brain. I don't even know the mass of the string. But I do know that MB is equal to 1,000 ms. That's what that part says over there. So another substitution has to be made. N over 2L1 square root 1,000 ms Ng L1 plus L2 over ms. Those cancel. Now it goes away. All that is left that we need to solve for is N, the number of brains. This becomes F squared, N squared over 4L1 squared, 1,000 Ng L1 plus L2. And that's it. There's nothing in the denominator. Now that I got rid of the square root, now I solve for N. 4L1 squared F squared over 1,000 N, oh no, the N stays up. 1,000 G L1 plus L2. And that is equal to N. Now, what are the units of n? N is, yes. Yes, thank you. And that goes in the numerator or the denominator? Denominator. Okay, there we go. So we have all of this. There's one last question that we need to ask, because I have L1, I have L2, I have gravity, I know I'm on the planet Earth. The one thing that I don't have is little n. But what I did do is I drew a picture. So which harmonic are we dealing with? You're on the right path. You're on the fourth harmonic. Antinodes are the same as the harmonic number. So this is 4. So 4, L1 is 3. There is a missing number. And this is also another thing why I'm proofing this. The frequency is not exactly given, but it is necessary. So I probably just said, 1200. Once again, I don't know if this is something where it could have been. This is as it came out of the printer. It may have been like a half hour before the test. I looked at it and went, uh-oh, I need an F. And I just forgot to write it down on the sheet of paper. N is 4. Because I don't know specifically which frequency we're talking about, we're going to get a, there's going to be a fraction of brains. I think when I wrote the numbers down that I wanted it to be a whole number. Ooh, and it worked out. I must have guessed. Part of my subconscious worked. 27. Whole number. So either A, I remembered it, or B, I got darn lucky. So that's the number. So that's the Walking Dead test. Bum, bum, bum. All right, so now what we're going to do is we're just going to go over problems, questions, anything that you guys want to talk about. The graders have been reminded that they need to get problem set 7 back today. I have not heard back from them, but so now. What do we want to talk about? Yes?
Can you do number 8 on problem set 9?
Number 8, problem set 9. I do think there is a bit of missing information, and so I'll correct that right now. You would think after so many years. Let's say that the distance between the trees is 7 meters. Does that answer the question for you guys? You didn't have the link? Yes.
If we did it, did the video say 5? Is it okay?
Oh, did I say 5 in the video?
Another video said 4.
And I watched the video that says 10.
All right. That just means one thing. I'm not going to grade number 8. But let's just go through it and show you. We'll just use 7 meters as the number. Every year I promise to fix that problem, and I guess I get distracted and then I don't fix it, and then I'm reminded again. So the cord is 650 grams. You've got, the tension is 240 newtons. The velocity is tension divided by lambda. Lambda is the mass of the string divided by its length. So velocity is T over MSL. And we get this. Now this string has a wave that goes to one tree and then comes back. So velocity is distance, which is 2L because it's got to go to the tree and back. So if the distance is L, then it travels 2L over the time that it takes for it to do this. So this becomes what T comes up.
Wait, why is it 2L again?
Because in the problem, the wave goes from one tree and then back in the problem. So the distance that the wave traveled is not L, it is 2L. But the L used in the velocity of the wave is L because it's based on, it's dependent upon its mass, linear mass density. So we get this. And now we could either bring in the L and do some canceling, or we can just plug and chug right now. 2 times 7, mass of the string, 0.65, tension 240, L is 7. And so whatever that spits out. Yes?
I know you just asked this, but I don't understand why 2L is pulled in front of the square root.
You mean how I went from there to there, or how I chose 2L? Yes.
For the 2L, it just says, how long does it take for the wave to travel from one tree to another?
Oh, then you drop the 2. I thought it was going to there and back. Okay.
Like, where does the 2L come from? Like,
Well, now I just got rid of it, so there is no 2L.
Well, why is there an L in front of the square root? I'm just kind of confused.
Velocity is distance L divided by time. Velocity is also known as the square root of T over lambda. So this becomes square root T over lambda is L over T. And lambda, and then we go on from there. So really what I did is I started with the definition of velocity, plugged in V from here, and then solved for T. Okay. Next question. Number 4? Okay. Now, with number 4, what I'm going to do is I'm going to save everybody a lot of trouble. And number 4 starts with a starts as a roulette wheel problem. So the solution that you have to do is you go through this to get that velocity. Because the one thing that you don't have is the velocity of the train, but you do have the frequency coming at you and the frequency coming away. So it's a moving source, just like the Daryl Walking Dead problem. So you go through all these steps to get that equation. So what I'm going to do is, rather than do this, rewrite this page again, we're just going to go boom, there it is. There's the answer. So you have to understand that a lot of times problems use the same solution in terms of getting to the equation. In this particular case, the towards is 3,000. The away is 2,400. And this is 350. So this becomes 600 divided by 5,400 times 350. 38.9 meters per second. That's the velocity of the train. You would go through write out those steps, and really what I'm doing is I'm requiring you're going to have to know this for the test. How do you do this? You just practice writing that solution down, do a little bit of algebra, and then you got it. Then you'll be ready for the problem. I've got to look for the source frequency. What is the frequency? And we will use towards. Yep. So this becomes 3,000, 1 minus 38.9 over 350. And I get that. That's the source frequency of whatever is being used. It was very interesting. One time, 2-3 years ago, someone presented me their notebook. I wasn't able to keep it, but they had tracked down every single problem set I had ever given in every single test and put it in a big binder. I was like, wow, that's amazing. I would love to look at that. The reason why I bring that up, this particular problem was originally like 4 or 5 problems, but it was like the 4 or 5 problems were all related to each other. Just went bam, 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 bam. And I decided one day, I'll just merge all 4 or 5 into one big paragraph. And so this is it. What is the velocity of the train? We answered. Using the velocity in one of the frequencies above, determine the frequency of the whistle. All right, we got that, 2667. If the whistle on the train was a half pipe, that the sound emitted was at its first overtone, what is the length of the whistle? So, frequencies for half pipes are NV over 4L. As a warning, the V in this particular equation is not the velocity of the train, it's the velocity of sound and air. So L is NVS over 4F. Now it's the first overtone. So what is the N value for the first overtone for a half pipe? 3. So 3 times 350 over 4, 2667. And I get a length of, writing it out in centimeters, 9.8 centimeters. I'll accept either of those units. If the whistle on the train was a pipe opened at both ends and its sound was emitted at the first harmonic, what is the length of the whistle? So we're switching whistles. Frequency is NVS over 2L. So L is NVS over 2F. We're at the first harmonic, so N is 1. 1 times 350 over 2 times 2667. And I get 6.6 centimeters. Now in the last part, the whistle on the train wasn't a whistle, but a guitar string of mass 20 grams and length 1.2. So this is a standard string, not an Atwood string. If the guitar was plucked and it was resonating at its fundamental frequency, i.e. first harmonic, what is the tension of the string? So we change things up a bit. Frequency is NV over 2L for a string. Velocity is tension over lambda. Lambda is mass of the string divided by the length. So velocity is tension length over mass. Plug this into there. F is equal to N over 2L square root of TL over MS. I have everything that I need. Solve for T. Square it. Bring that up. And that equals that. So that, yes. You're welcome. So now I get 4, 2, 6, 6, 7 squared. The length of the string, 1.2. The mass of the string, we're going to have to use kilograms, 0.02. It's at its first harmonic, so 1. And it's a big number, but big deal. 6.83 times 10 to the 5th newtons. And that's the tension. Now, in terms of problem 4, the first part will be on the test. It's the Doppler shift problem. But the stuff behind it, the only thing really that you need to know how to manipulate is the frequency of the string. Pipes will not be involved in the problems of appetizers because I got other things to worry about. But they could be on multiple choice. Yes?
Could you look number 11?
Number 11. Oh! Okay. 11 is fun. So in number 10, it's effectively really what we're doing. Number 10 is like, or 10 and 11 is like this. So what we have here, oh no, I take it back. No, this is a better one. Oh, this, okay, I got this. It helps if you actually read the problem. So it's an Atwood string problem. A pulley is 1.2 meters away from the wall. So L1 is 1.2 meters. This is L2, and L2 is the remainder of the string, which means it is 3 minus 1.2 or 1.8. I'm not sure if we're going to use this. I said that the 3-meter string has a mass of 28 grams. So the mass of the string for the whole string is 0.028 kilograms. At the end of this string, the hanging mass is 40 kilograms, and it's iron. Now, the tension in the string comes from the sum of the forces in Y, which is 0, which is T minus mhg. So the tension is hanging mass times gravity. Iron will become more relevant in problem 11, but I have to do number 10 just to show you what's going on. I want to know the first, second, and third harmonics. F is NV over 2 L1. L1 is the vibrating length. The velocity is the tension divided by linear mass density. N over 2L1. The tension is the hanging mass times gravity. Lambda is the mass of the string times or over L1 plus L2. Or you could just substitute in 3. It doesn't really matter. Now, when N is 1, you're just left with 1 over 2L1, hanging mass, gravity. I'm just going to substitute in 3 right there. And the mass of the string. So this becomes 1 over 2 times 1.2, hanging mass 40, gravity 10, L1 plus L2 3. Mass of the string 0.028. And you get a frequency of 400 times 3 divided by 0.028. I'm going to square root that guy and then divide by 2.4. So I get a frequency of 86.3 hertz. Now, one of the things that you can see is that this is when n equals 1. You can have the relationship that f of n is equal to n f of 1. If you just factor out the n, what's remaining is the frequency when n is 1 anyway. So you can express it like this. So f of 2, the second harmonic, is 2 times 86.3, and f of 3 is 3 times 86.3, or whatever that is. I'll leave it to you. You got to do something on the problem set. The thing that changes with this is the iron mass when it is hanging here, that tension is simply MHG. Yes.
Can you move that over a little bit?
Sure. The tension is simply MHG. If it's resting in water, the tension is going to change. It's going to be T prime. You still have hanging mass and gravity pulling down, but now you have a buoyant force pushing up. The tension on the string will lessen. Some of the forces in Y are still zero. That thing is still going to sit there. But here you have buoyant force up, new tension minus hanging mass, gravity down is equal to 0. So T prime is equal to hanging mass, gravity minus the buoyant force. That buoyant force is rho water, V, and G. V is the volume of the object, and because it is fully submerged, I could use V sub D, but V sub D, the displacement volume, is the same as the total volume. But I don't have the volume of the iron. But what I do have is the knowledge that it is iron. So Swiss Army knife this. Hanging mass divided by the density of iron. So this equation here, T prime, becomes MHG minus rho W MH over rho FE G. And that is the new tension. And in fact, what I'm going to do is I'm going to solve for it now. T prime, hanging mass, it's 40. (10) minus 1,000, 40, 10, and then I knew I was going to have to use this. Iron and steel, 7,800. There have been times where I ask Siri, but Siri is currently busy recording the video. And I get a new tension, instead of 400, I get a tension of 348.7. So that particular number, when you go, well, what number does it replace? It replaces the MHG. It replaces that 40 times 10. Because technically what happens in here is that 400, which is this, now changes to 348.7. So it becomes F1 is 1 over 2 times 1.2 square root. Instead of 400, it becomes 348.7 times 3 divided by 0.028. So the frequency is going to drop just a touch. And instead of 86.3, we have 80.5 hertz. And you do the same thing for F2 and F3. F2, 2 times F1. F3, 3 times F1. And there you go. And that is your 10 and 11. It's a fun. The thing about the Atwood string one, would I put, just thinking out loud about it, we already got a problem entirely dedicated to fluids. Put the fluids part of the problem onto this, I think maybe asking a bit too much. I'm leaning away from it. So we're gonna have a buoyancy or Bernoulli's equation problem. The Atwood string, make it clean. I'll do some, I don't know what I'm gonna do with it. It may just be the boring Atwood string that we've always had. And then Doppler shift. Yes, or no, you're number 2 because you were rude and snapped your fingers at me. She's number 1. You have the question, don't you?
Yeah, I was just gonna ask if you could do
Number 5. What's your question in the back?
Oh no, I was like, maybe when you was-
Oh, okay. Oh, it wasn't an insult. Okay, I take it now as a compliment. Excellent. Number 5. Okay, in this particular problem, it's the same thing as the 5 is very similar to 10. The pulley is 1.8 meters away from the wall. A 4-meter string that has a mass of 25 grams. So the total length, L1 plus L2, which is what I really need, is 4. L1 is 1.8. The string has a mass of 25 grams, 0.025 kilograms. I don't know how that works. Kilograms. Iron mass is hung from the end of the string hanging off the pulley. When plucked, it produces a fundamental frequency of 2,000 hertz. What is the mass of the iron? Oh, and then we go to the moon. Excellent. So the first thing that we got to do is we got to figure out the mass of iron that's hanging. We do the same derivation. Sum of the forces vertical is 0, which is equal to T minus hanging mass gravity. So T is equal to hanging mass times gravity. The frequencies are NV over 2L1. L1 is the vibrating length of the string. The velocity is tension over linear mass density. Linear mass density is mass of the string over L1 plus L2. The tension is the hanging mass times gravity. So F equals N over 2L1. Tension, hanging mass, gravity, lambda ms L1 plus L2. And I get this. I have everything with the exception of the hanging mass, so we're going to find out what that is. Solve for hanging mass, square everything. And then solve for hanging mass. So this becomes 4, 1.8 squared. F is 2,000 squared. MS 0.025. N is 1 because it's a fundamental frequency. G is 10. L1 plus L2 is 4, because that's given. That's the total length of the string. Starting really in the spring semester this year, I was really on a big kick on really making sure that the test numbers work out right. And not only work out right, but cancel a lot. 32,400 kilograms. Now, once again, people ask, well, dude, you got a 25 gram string and you got 32,000 kilograms hanging off the end of it. How can that string not snap? It's made of rebellium. It can handle it. Let's not worry about that. If it was made out of stadium, or Starkvillium, that Starkvillium stuff is it's crud. It won't hold up to anything. So that's the mass that's hanging off the end. And the next question is, take the mass and experiment to the moon and find its first overtone and third harmonic. Okay. Well, we've already solved it to get the frequency. F is N over 2L1 square root hanging mass, but now G is replaced with G prime. G prime is 10 divided by 6. Moon gravity is 1/6 of Earth, so it's just 10 divided by 6. Now I'm looking at first for the first overtone and third harmonic, but what I'm going to do is I'm going to find the fundamental frequency and then I'm going to deal with it. So N is 1, 2, L1 is 1.8, square root 32,400, 10 divided by 6. L1 plus L2, that's the total length, or 4. Mass of the string is 0.025 kilograms. And then we get (816.5 hertz). That's the fundamental frequency. Now, as I've shown you before, F of N is equal to N times F of 1. So I'm looking for the first overtone and third harmonic, which means that you have to find F2 and F3. And there you go. And then it's just plug and chug from there. And so that's the problem for 5. 5 is kind of an interesting twist because you add gravity to it. Could I put it on the moon initially and then ask for the frequencies and stuff? I could be. I don't know. It doesn't sound too exciting. So, I mean, it's fairly obvious when the professor goes, ooh, ah, then you know you're looking at a problem that could be on the test. And I'm not going to get burned by negative pressure ever again. So the numbers are going to work. Next question. If we can kind of hold it together for about 15, 20 minutes, then we can leave. Yes?
What did you say the appetizer, like, is supposed to be seen with?
As a review, metaphysical certainty for the three problems. One is fluids. It's really going to break down into one of two things. Something to deal with Bernoulli's or buoyancy. Not beyond, but buoyancy, whatever that is. Atwood string, which is basically sound, and then Doppler. Most likely the roulette wheel problem of that caliber. The appetizer will be oscillations. So the appetizer that we did today with the zombie is a great example of what could be an appetizer problem on the test. I may try to do something else and make it, I don't know. I haven't decided what I'm going to do with that one. But it's going to be either a simple pendulum, a spring pendulum, or both in some way. And I don't know. It's just, it can't be as complex as a real problem. So it's going to be one of those, an average student should be done with the appetizer in under 5 minutes. Probably closer to 3 if they know what they're doing. And so that's the answer for that. Yes?
We did a problem history on the test. That was, the units provided by 1/2 rho b squared without any conversion is. Can you do that?
So the what I asked about is you're going to get like on Bernoulli's equation, you're going to get a term like that, 1/2 rho v squared. And the question is, what unit naturally gets kicked out of 1/2 rho v squared? Rho's units are kilograms per cubic meter. And velocity is in meters per second. And since it's squared, you do that. The trick is not to cancel all of the numerator with some of the denominator. You're only going to cancel one of the meters. So one of those is going to cancel with one of those, and you're going to have an m in the numerator and an m in the denominator. Rearranging this, you get kilograms meters per second squared and 1/meters squared. That kilogram meter per second squared is a Newton. So the natural unit getting kicked out of that 1/2 rho v squared is a Newton per meter squared. You can do the same type of unit analysis for rho GH, and you end up with the same thing, Newtons per meter squared. You're welcome. That's a good question. I'm a big fan of units. That's why if you get the Bernoulli's equation, you have to know that there is a conversion either from Newtons per meter squared to atmospheres or the other way around. Yes? Yeah.
Okay, so when you use the n times v over 2l and versus 4l, right?
Mhm.
You use 2l when it's a string or just a...
So So the two equations are NV over 2L and NV over 4L. This is only used for the half pipe. The string and the full pipe use the 2. And really, the question is, where does the extra 2 come from? It comes from the derivation. And we don't go into it, we just don't have the time. So let's just accept it for what it is. So that's it for that.
For pipes, it's the velocity of sound, but for string, it's the
Yeah.
velocity of-
For a string, that velocity is the square root of t over lambda. For the full pipe and for the half pipe, the velocity is 350.
And I noticed on the tests, when you look at the formula section,
Mhm.
they don't, I mean, they didn't use buoyancy on those tests, but if we were to have that on ours, would we have that?
I would give you the equation.
Okay.
If I do a buoyancy problem, the equation should be on that sheet. And if I don't give it to you and I do a buoyancy problem, I don't even see any problem if I don't give you buoyancy. I would still put the equation up on the board. So I need to remember to add that. I'll look at that. We don't have to memorize all the densities of every single element known to man. They will be given to you when necessary. Or I'll ask for the density, ask you to solve it. Whenever you have a buoyancy problem, have that equation on standby, because most likely you're going to need it to substitute something out. I've got a feeling that most likely these are going to be, if it is a buoyancy, it will be fully submerged in whatever. There won't be a partial submersion. Because we never really, we did a few, but we didn't do all of them.
So like the one we practiced yesterday, like with the balloon and the water.
Mm-hmm.
Okay.
Yeah, it's either gonna be a balloon, like a balloon filled with gas in air, or a balloon filled with some substance in water. Most likely it will be a situation where you do have to pay attention to the density of the material inside the sphere. I don't try to get cute on tests, so it's gonna be a straightforward power buoyancy problem. Yes. Oh, you're just doing your fist bump again. Excellent. Yes. Trying to think what else. Know those naming conventions. For a, all right, then we go, you've got a half pipe, give me the first 3 harmonics by name. So I'll give you the first one. First harmonic. What's the next one? Third harmonic. What's the next one? Fifth harmonic. Now, give me those same frequencies, but don't use the harmonic system. Use the overtone system. So the first harmonic is what? Fundamental frequency. What's the next one? First overtone. So it goes fundamental frequency, first overtone. What's the one after that? Second overtone. So for the overtone system, it always goes fundamental frequency first and then second overtone. For a half pipe, it goes first, third, fifth harmonics. But for anything else, then it's the usual first, second, third, etc. Linear mass density has what units?
kilograms per meter.
Kilograms per meter. And don't say it as a question. saying as an answer. This isn't Jeopardy. I would even accept what's the units of linear mass density as elephant. It's wrong, but you said it with confidence, and really that's one of my prime lessons in this class. Yes.
I have a question.
Mhm.
I can't remember if you did this one yesterday, but are you gonna do a spring one where it's like K equals F over L and you have to like substitute a bunch of stuff, like where it's like.
I mean, that could be for the oscillation problem.
Okay.
The
So like substitute where it goes like. K.
like a potential spring. I mean, just sitting here thinking about it, you've got a spring, and you know that this distance from its rest position to its hanging position is 30 centimeters when you have a 5 kilogram mass hanging on it. The question would be, you set this thing to oscillate, how long will it take to oscillate 10 times? That's a really legit appetizer problem. So T for N equals 10. For this particular case, you're going to need to know Hooke's law. F is equal to Kx. You're going to need to know that the sum of the forces when it's hanging, it's in translational equilibrium, so it's equal to 0, which means that it is equal to Kx up minus mg down. So mg is equal to Kx. And then let's see what else that we need. Now, I didn't specifically ask for the spring constant, so we don't have to solve for K and get a number. What we can do is I need time for when the number of oscillations is 10. So period is equal to 2 pi m over K. The period is T is equal to N times the period. So the total time is 2 pi N m over K. In this particular case, we know what m is, we know what n is, we need the total time. I don't know what K is. However, mg over x is equal to K. In fact, it's unnecessary to have the mass for this problem, because when you plug it in, 2 pi n square root of m over K, which is x over mg. The masses cancel. And you know how I am about a big fan of not giving you numbers because you don't need them. So most likely for a problem like this, I would just go, you got a mass on it, it stretches 30 centimeters. Set this thing to oscillate, how long would it take to oscillate 10 times? And I promise you, 3 people will come up and say, but you didn't give us the mass. And my answer will be, and this is really interesting. This is going to get philosophical for a moment. When you come up to me and you ask me the question for this problem, and you say, you did not give us that mass, and my answer is, it is a correctly constructed problem. Right back at you. What does that mean? What did I just communicate to you? You don't need it. Because I have rules. I have to be true neutral during this test. I can't really help you unless I make a mistake. So, in a way, I'm telling you the answer by not telling you the answer. Very zen, I believe. So, this gets plugged in, 2 pi n x over g, 2 pi 10 0.3 over 10, and that gives me .9 seconds. And that's a great problem because I know it upsets the plug and chuggers no end. And I'm all about that. If you see the light and adopt the alphabet soup method, the tests are going to go a lot easier for you. Especially for a problem like that. That problem was built to frustrate plug and chuggers. Kind of excited by it. Does that mean it's on the test? I don't know. Does it mean it won't be on the test? I don't know. Or am I lying? Or am I lying about lying? That's the truth. Just a couple more minutes. Do you have any other questions? Okay, we only have one individual who got 100s on the first 2 tests. I will be grading that test individually and thoroughly. So don't worry, there won't be a trifecta this semester. I think that's it. I'm nearing the end. All right, anybody want to stay here and talk physics? Okay, good, let's get out of here. Homework due at 6. Tutors in tutoring room from 1 to 6. Have fun.